All right. So today, instead of doing any new lectures, I wanted to post a video sort of going over some of the review problems in the worksheet that I gave you that isn't due until Friday. Again, this is going to be just like the review problems in the past. I'm just looking for you to really submit it. I've given you the solutions today. They're posted right now. So it's not about the solutions, it's about giving you some problems to work. So don't feel like you have to do all of them, but they're there for you to study. So, um, so I'm going to sort of go question by question. I won't go in a lot of detail in some where I think the solutions are pretty straightforward. And then others I'll go into more detail where I think there would be more questions on. But again, if you do have questions, send me an email, post to the discussion board, and I'll get back to you as soon as I can. Okay, so let's look at the first problem. So the first problem, I've kind of broken it up into sections. So this one is from pretty early on, looking at conductivity. And so this actually has some overlap with the last content as well. So this is asking you to find the charge carriers per unit volume for zinc selenide, which is an intrinsic semiconductor, so that's important, and then at room temperature. So I've given you the band gap, and then also the effective masses of the electron and electron holes here. So here, if you look sort of over at my solutions here, basically the approach that we have is down here, you'll see that if we're trying to get N or P, which is the number of these charge carriers per volume, we can get that by looking at the density of states for either the conduction or the valence band, and then the exponential of the band gap over 2kT. That was kind of our basic equation for solving for N or P. And so we need to find those density of states first. And so if we go back to those equations, that's the first thing I've done is solve for the density of states, putting in the effective masses, and then the constants H, K, and then plugging in the temperature as well. And that should give you the density of states. And then plugging that in along with the band gap. So here I've converted to joules so that my value of K is in joules. So make sure you keep the units straight on that. And so there I get the number of charge carriers. So this, in this case, since it's an intrinsic charge carrier, that's why I have N equals P in this case, not N times P. Because it's intrinsic, so those should be equal. And so they equal 135 per meter cubed. And so again, based on what we've seen, that's a pretty low number to have per meter cubed. All right, so that's all this question is asking for, is asking for the charge carriers per volume. But we did talk about conductivity as well, so keep in mind how to calculate that if given mobility and so forth. All right, so on the second section, it's asking about fracture toughness. And so this, we had some example problems in the lectures about. And so the first part is asking you to calculate the critical stress intensity factor, so fracture toughness, for quartz. And so again, if we go to the solutions here, you'll see that I've given you the equation, so that one part of the K1C formula, which is dependent on the capital Y, which we know to be Young's modulus, and then the surface energy. So in these cases, we can look up these values if they're not given in the book. So I know some people express some difficulty finding this number, so I posted it on the discussion board. But you can typically find tables that have this information, and so I got 287 millijoules per meter squared for the surface energy of SiO2, and then the elastic modulus of 94 gigapascal. So putting those two numbers in, I've converted to SI units so that it's Pascal meter to the 1/2. And so then I've converted to be megapascal to meters 1/2 because that's a more common unit. So that's 0.232. Then the other side of the expression, which is equal to K1C, is the fracture stress and the stress crack length, critical crack length here. And so that's how we're getting the second part, because that's asking about the tensile stress level at which it fails if we have a crack of 50 microns. So basically plugging in for 50 microns for C critical, and then the stress intensity factor that we just calculated, rearranging to solve for this stress value, we get 18.5 megapascals because all of those expressions were mode 1 or tension. All right. And then the last part, we talked about bend testing, and I gave you some expressions for the modulus of rupture. This also should look familiar from the lab, so you should be quite familiar with this. And so given that stress from above, and given the spans and the diameter, we can rearrange and solve for P, which is the load, which is what it's asking for. Load is the same thing as force here. So we get 45.5 newtons. Okay, so questions 5 and 6 are still on fracture toughness, but they're alluding to some of the methods we talked about for toughening. And so the first one's asking about crack bridging. So it's asking why debonding is important. And then the second one's asking about the mechanism for partially stabilized zirconia. And so these are things that, you know, I put some information from the textbook as solutions to these answers. This is something that you should be able to sort of answer based on our discussion, and also our also your reading on the section on why that's important. So we talked about both of those in the lecture. So I won't sort of expand too much other than to just kind of point you to those sections in the textbooks. And let me know if you have any further questions on those. Excuse me. Okay, so you'll notice when you look at the solutions for section 3, ceramic processing, I didn't give solutions here because this is a case where there could be multiple answers if you've justified your choice. So we've talked about some forming or shaping methods on these, and so I want you to basically choose one of those that we've talked about and see if you can justify your answer. And so based on what this is and what type of material it is, what the general shape of that object is, you should come up with one of these forming methods and then justify why you chose it. And so as long as your justification is good, then that should work. So just as a couple examples, for a vase, vases tend to be hollow, right? So you can put flowers and stuff in them. And so we talked about slip casting, which is well equipped to make hollow objects. And so you could specify slip casting and then talk about that being useful for hollow objects. And that would be an appropriate answer. Same thing for let's look at B. If it's looking for a flexible plastic disc with a thin film of iron oxide for memory storage. So this is a technique that's actually done to make CDs and things like that. We talked about, really, we only talked about one method for forming thin films. So if you mentioned tape casting and then talked about how with tape casting you can apply thin film on any substrate, then that would be an adequate expression. The same thing for the other two is as long as you pick a forming method that is applicable to that shape and give your justification for it, then that is fine. All right. So I believe that most of your questions will probably be on this section 4. So that's where we're going to spend most of our time. So let me go ahead and sort of switch over here. And so what we'll do is I'm going to walk you through some of the questions. Keep in mind, if I don't fully answer them in this video, I've posted the solutions, so maybe have those up while you're looking through this. But I'll try to give you, sorry about that, I'll try to give you the overview and the strategy for solving these problems, and then the solutions will be provided in that document that's been uploaded to Canvas. All right, so now looking at question 8, which is in section 4 on ternary phase diagrams. I assume this is where a lot of the questions are going to be. And so the first question, 8, in the section is on compositions. So I've labeled 2 points, X and Y, and I want you to come up with the composition. So composition is always going to be in terms of the components, and there are 3 components because it's a ternary phase diagram. And in this case, my components are A, B, and C. So I'm trying to get the number, the amount of those components. And so you can kind of notice already that the axes are in weight percent, and so it should be in weight percent A, B, and C. And so this is where we're going to draw our lines through the point and parallel to each of the bases. And so for if we just sort of quickly go through how we would do X. So let me go over here to the PowerPoint where I've got the image. So this is where what I did was create a line and make that line the same as the axis. So as close to it as I can without this autocorrect. All right, just so you can see a little bit better, I'll make it red and a little bit bigger. So I've made it parallel to this base of AC. And so now I'm just going to move it so that it goes through the point. Right, so that's pretty close. And I'm going to do the same for the others as well. So if I make another line, and this time I'll make it parallel to CB, and then make that go through X again. And one last time, have it parallel to AB. And then go through X. All right, so from here, I'm just going to read off the amounts. And so if I want to get the amount of A, I'm going to look for the line that is parallel to the base BC because it's opposite. And so this that's this one. And so if I look at that line, where it intersects either axis is okay. This one says weight percent C, but since this one already says weight percent A, I'm going to go ahead and use that. So if I read this off, then it looks like it's going to be 40, and then this is 1, 2, 3, so about 43 weight percent A. And then I can do the same for B and C. So let me go back to my solutions here. And you'll notice for X, I got 44 here. So there is going to be some slight variation sample to sample, depending on how you drew your lines. So you'll notice the solutions are back when I had a paper version of this. And so that's how I did that version. And so I got 44 weight percent A compared to the 43, so that's pretty close, and then 12B and 44C. So again, and then double check to make sure that adds up to 100 or is at least very close to that. And then you can do the same for Y. And so that's how you're always going to get the composition of a given point. Okay, so now let me go back to the next question. So for 9, it's asking you to identify the invariant points, and those are, it's already labeled as U and W. And it wants you to identify them as eutectic or paratectic, and then it wants you to give all the phases that are present at equilibrium for those. And so just real quickly, let's sort of go through this one. So there are 2 methods to determine if it's paratectic or eutectic. The first one I told you about was using the slopes of the boundary curves. So if we focus on W here, all of the slopes of these boundary curves go towards W. And so that means that all the boundary curves slope down in temperature to a point W. And so that is a eutectic. So we know W is a eutectic. And then if we have any variation in that where one or more goes away from that point, then we know it's a paratectic. And so U here has 2 going down, but this one over here goes up. And so that's a paratectic. So that's the first method. And so you'll see in my solutions, that's what we have. U is a paratectic, W is a eutectic. So the other method is to determine the compatibility triangles. And so you'll see here this dashed line already gives us that. And so we're going to have another exercise with compatibility triangles. So I'll talk about that more in a second. But the basic idea is if the invariant point is within its own compatibility triangle, as W is, then it's a eutectic. If it's outside, like U is, which has its compatibility triangle over here, then that's a paratectic. So you can do it either way. If you have arrows, you can use those. If not, use the compatibility triangle method. So otherwise, it's going to have you determine the phases present for that. And so that is going to be listed here. So both of them will have liquid. And then in this case, they both have 3 solid phases. So for the paratectic, we have A, B, and BC. So that's basically what's around this invariant point. And then the eutectic, we have the same thing. We have a liquid, and then we have A, B, C, and C in this case, or what's around that point. Okay, so let's go to the next question, 10. So 10 is asking you for each invariant point that's listed to write the reaction upon cooling. So basically we would need to know if it's paratectic or eutectic and then write what it is. List the temperature, so the critical temperature for that reaction. And then also draw the compatibility triangles. So I would probably start there. Draw your compatibility triangles. Here we see 3 invariant points. So if I kind of go over here to the solutions, I'll see 1, 2, 3. I've labeled them as such because we have boundary curves, 3 boundary curves meeting at a single point. So those are our 3 points that we have. And then, like I said, even though it's the last one, I would probably draw my compatibility triangles first. So in each of them, the procedure is the same. For example, if I move over here to the other diagram here, if I look at the invariant point 1, I can use the arrows again, but I can also use the compatibility triangles. And the way I'm drawing those is to identify the primary phase fields around it. So TiO2, ZrTiO4, and Al2TiO5. And I find the composition of those. So TiO2, and then ZrTiO4, which is here, and then Al2TiO5, which is here. And so basically this triangle bounded by this line is the compatibility triangle for 1. And so 1 lies within that compatibility triangle. And so I determine that. For 2, if you go through the same method, you'll see that this sliver in the middle is its compatibility triangle. And then this is outside of it. So it's a paratectic. And then this region over here, which is the compatibility triangle for 3, and 3 is within that. So it's a eutectic. And so that gives us what we have and gives us our compatibility triangles, and that allows us to determine that. So for those reactions then, so let's start at 1 and 3. So it's obviously upon cooling, going to be a liquid goes to the 3 solid phases for eutectic. So liquid goes to those 3 solid phases, and same thing for 3 as well. So liquid goes to 3 solid phases. We know it's eutectic on both of those, and the temperatures are given by the temperature on the diagram. So that's listed right where the invariant point is. So that's where you're getting that number. And the last one is 2, And so this, to determine how you get this reaction with this paratectic, remember we have those crossing tie lines that we're trying to construct. So going from the 3 solid phases and using the point here as the composition of the liquid, we can construct 2 crossing tie lines where we have liquid here, and then we also have the composition of ZrO2, and so those crossing along with the ZrTiO4 and the Al2O4. So let me draw that real quick for you because that one's a little difficult to see. So let's go to the PowerPoint again. And I've got the diagram up here. So we know that we have, for the paratectic, we know that we have, let me go back real quick. We know that we have this reaction. We know that those are our solid. We know our solid phases, ZrO2, ZrTiO4, and Al2O5, because those are what surround the invariant point, right? So that's how we're getting those. And so we look for the compositions. So this is the composition of ZrO2. This down here is the composition of Al2TiO5. What else do we have? ZrTiO4, that's the other one. So those are our 3 solids involved. And then our liquid at the paratectic would have a composition here, because this is our paratectic point, right? Excuse me. So what we're going to basically do is we have to construct 2 tie lines that would cross, and that determines our reaction. So let's, for example, say that I want to cross these. So that would leave the other 2 as the other reaction, right? So if this was correct, and it is not, just to give you a heads up, if this was correct, then our reaction would be liquid plus ZrTiO4 goes to ZrO2 plus Al2TiO5. Excuse me. But that is not correct, because the purpose of this is we're trying to cross these lines. And that crossing tells us that we're consuming one thing upon cooling, which is the liquid and the other solid, and we're producing the other 2. Excuse me. And so the only way we can do that is if we, for example, have ZrO2 plus the liquid, and then we have the other 2. See, these 2 now cross. And so this tells us correctly that we have liquid plus ZrO2, and then those are the ones that are consumed, and they're producing ZrTiO4 and Al2TiO5. And it tells us the amounts here of this line, and then this section and this section tell us how much, relatively how much, is being consumed of each of those phases. All right. So the last 2 questions on this, 11 and 12, are somewhat related. And so the first one is asking us to sketch and describe the crystallization path. So that is the composition of the liquid starting at A. And so it's asking for each segment along the line to list the temperatures, phases present, and the overall reaction. So just kind of like you saw in the slides that we went through this. Okay, so if we start, and I'll sort of switch over here to the PowerPoint so you can see it more clearly, but if we switch over here and we see A, so A is right in between the isotherms for 1850 and 1800. And so that means that it falls on isotherm, there would be 1825 approximately. So that means that above 1825, that this composition would be 100% liquid. And so the composition would be the same as point A. As we get lower, it's going to be in this primary phase field where we start to have Al2O3. And so that's the phase field it's going to be in. And we know the liquid is going to change composition as we form more and more of the solid. And so it is going to follow a tie line between the composition of the liquid and the solid. So the solid has a composition of Al2O3, so here. And then it's going to be a tie line between that. So a line between those, and then it runs through A as well. So that's why I've made this dashed line to kind of illustrate where that line is going to be. Because it tells me that initially my liquid is going to have a composition of A, and then it's going to run along this line, the composition of the liquid, whereas the solid maintains its composition over here. So the liquid, basically, the liquid composition goes away from A along this tie line that I've drawn. And so if I draw that in, very roughly, that would be from point A, and let me change the color here. So going from A, my crystallization path would follow this line and keep going until I get to the next significant point, which would be the boundary curve. And at the boundary curve, that is where we start to form a second liquid, which is Al2TiO5. And so at that point, it's going to follow the tie line. Or sorry, it's going to follow the boundary curve at that point. So it's going to change direction, and the liquid is going to follow the boundary curve until we get to the next significant point, which is down here at the eutectic point. Because if we look at the arrows, and we're looking at the same phase diagram, so this is a eutectic point. And so at that point, at 1610, it goes through the eutectic reaction. And so now let me sort of switch over and go to the solutions for you. So for 11, and that's what I have written here. So starting at A, segment 1 is the two-phase field, 2 is the boundary curve, and then 3 is right at the eutectic. And so here I've just kind of described all of that for you, what we've just gone through. So above 1825, it's liquid. Between 1825 and about 1700, it's going to precipitate Al2O3. And then the boundary curve is about 1700 until 1610. That's where we form the 2. And then right there is where that reaction. So that's what the question's asking for, is the crystallization path, but also a description of what's happening in each area. Okay, so the reason I said these are connected is because the next question is on the same diagram, and it's asking us for the same composition. It's asking us for the amounts of phases present at 1650. So if I go to my answers for the previous question, and if I look at the segment that would have 1650, so I'm looking at 2 here, it tells me what's going to happen. It tells me in that region, I'm precipitating these 2 solid phases from a liquid, right? So this is my reaction. So it tells me I have 3 phases present. And the crystallization path itself tells me what the composition of the liquid is going to be. So let me switch back over to this. And so we're looking at 1650, right? That's the temperature of interest. So if I follow this line back, so that's going to be somewhere around here, right? So, and let me switch just to give a little bit better. So this point on the crystallization path is 1650. So what this point tells me is the liquid composition. So that point at 1650 is the composition of the liquid. So, but I also know I have this phase and this phase, right? Those two, because I'm on this boundary curve. So I know that I'm going to have, and then the compositions of those phases are here for Al2TiO5, and then Al2O3 is down here, right? So I have the composition of those 3 phases, and so to get the amounts, I draw a triangle containing those 3 compositions. So if I draw a quick triangle from those 2 points, and then from here. And then fill in the last one. So now I have the 3 compositions of the phases I'm interested in finding out weight percents. I have my overall composition of my material. And so I can use that to determine the weight percents or weight amounts. And that's what I've done here on the next one in the solutions, right? So I've created this triangle. And the next step is to make those lines parallel to each of the bases, right? And then projecting all on one length, I have X, Y, and Z. So X being opposite of the composition of Al2O3 is going to give me that amount. So X over X plus Y plus Z, right? So I can get that. And then Alt2TiO5 is opposite of Z. So that's where I use Z. And then right in the middle, that leaves us with liquid. So that's going to be Y. And so I can use those amounts, these lengths, X, Y, and Z, to give me those amounts, right? So that's how I use the ternary lever rule in this case. And so that's what this problem is asking you about. If it asks me a question, so let's go back to the next section. If it asks me a question about section 1 here of the crystallization path, I know that I have 2 phases present, Al2O3 and liquid. And so I can use the binary lever rule. And so you can go back and look up how to do that in the slides. And then at 3, if we're below 1610, we no longer have liquid. And so I know what my 3 solid phases are. And so I can use that triangle along with my composition A to determine what phases I have. And so that's kind of the overall process of how you're going to look at, use these crystallization paths and also determine weight percents as well.